Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder why it is so hard to know if a new medical test or treatment will actually work when you need it most? This paper tackles that exact question, and it is super important for any of us who've ever hoped for better mental health care. So here is the big idea. Precision psychiatry wants to use things like brain scans or genetic tests to figure out the best way to help people with mental health issues. It's like getting a super personalized plan. But a huge problem is that the way scientists usually test these tools doesn't quite match up with how they'd actually be used in a real doctor's office. This paper introduces a new tool, the E2P Simulator, to help researchers think about whether their findings will be truly useful in the real world. It's all about looking at not just if something detected an effect, but if that effect is big enough and reliable enough to make a real difference. For a long time, scientists have been searching for reliable biomarkers, things like specific patterns in brain scans or unique genetic markers that could help diagnose or treat mental illnesses. The dream is precision psychiatry where care is tailored to each individual. But despite all the research and exciting new tech, actually bringing these tools into clinics has been really tough. Many promising findings haven't held up, and even when studies report high accuracy with these prediction models, a closer look often reveals issues like over-optimistic results from small studies or flawed testing methods. The paper argues that the big reason for this is that typical scientific tests are focused on finding any effect, not necessarily on how big or useful that effect is. Plus, they often don't properly consider how reliable our measurements are. If your measurement tool isn't perfectly consistent, that weakens the signal, and a weak signal becomes even weaker when you try to build a prediction model. This section dives deeper into why just finding a statistically significant result isn't enough. Think of a p-value as a fluke meter. A low p-value means it is unlikely the result happened by pure chance. But that doesn't tell you if the effect is big enough to matter in real life. Imagine a study finding that people who eat one extra grape a day are statistically significantly less likely to get a cold. That is interesting. But is it a practical improvement? Probably not. The paper warns that as datasets get huge, even tiny, practically useless effects can become statistically significant. Here is where it gets really interesting for me. Measurement reliability is key. If you measure something 10 times, do you get roughly the same result? In psychology and psychiatry, many things we measure, from cognitive tests to brain imaging patterns themselves, aren't super reliable. This unreliability acts like a fuzzy filter, weakening the true signal. The paper explains how this attenuation makes effects look smaller than they really are. This is especially bad when trying to predict outcomes, because a weaker signal means a weaker prediction. They even give equations showing how much an effect is weakened by unreliable measurements. Even when scientists report how big an effect is, like using Cohen's d, people often struggle with what it means practically. Using simple labels like small, medium, or large isn't always helpful because those terms are quite arbitrary and don't directly translate to clinical usefulness. The paper emphasizes that for clinical translation, we need to understand predictive performance, not just abstract effect sizes. So how do we understand predictive performance? The paper talks about metrics like sensitivity and specificity. Sensitivity is like asking, of all the people who actually have the condition, how many did our test correctly identify? Specificity is like asking, of all the people who don't have the condition, how many did our test correctly say don't have it? These are important, but they have a blind spot. This is a crucial point. Metrics like sensitivity and specificity don't care about how common the condition is in the real world. They are invariant to outcome base rates. Imagine a rare disease. Even a test that is pretty good might flag a lot of healthy people as sick, just because the disease is so rare to begin with. This is the famous false positive paradox. The paper explains that we really need to consider the base rate, which is the actual prevalence of the condition in the population we're interested in. Without considering the base rate, even a seemingly accurate test can lead to many mistakes in practice. This section introduces decision curve analysis, or DCA. It is a way to evaluate how useful a prediction model is from a clinical decision. Making perspective, it tries to balance the benefits of correctly identifying cases against the harms of wrongly labeling healthy people as sick. However, just like with other metrics, DCA can be misleading if it is based on studies that artificially balanced how many healthy and sick people were included. The paper stresses that we need to adjust these analyses for real-world base rates. And here is the solution they developed, the E2P Simulator. It is a web tool designed to fix these problems. It allows researchers to do what they call predictive utility analysis. This means they can input their initial findings, like the measured effect size and reliability, along with the real Zen world base rate. to see what the actual predictive value and clinical usefulness would be. It is like having a simulator that shows you how your discovery holds up in the messy real world, not just in the controlled environment of a lab experiment. They compare it to power analysis, which helps researchers figure out if they have enough participants to find a statistically significant result. Predictive utility analysis helps figure out if a result is significant enough to be practically useful. This is where they put the simulator to work with examples. First, they look at a hypothetical cognitive marker for depression. Imagine a marker that shows a large effect size of 0.8. That sounds great, right? But when they plug in the real-world prevalence of depression around 8% and the unreliability of the diagnosis itself, which is actually quite common, only a 0.28 reliability in field trials for DSM-5. The picture changes, the accuracy metrics looked okay, but the actual real-world usefulness, like the ability to correctly identify people who have depression without too many false alarms, ended up being quite modest. They also highlight how much better things could be with just better measurement reliability, showing an example where improving consistency dramatically boosts predictive performance. Next, they demonstrate with a real Zen-world example, a biomarker for Alzheimer's disease called p-Tau REOTCIA. This one was actually cleared by the FDA, which is a major accomplishment. They use the reported high positive predictive value and negative predictive value, even though this is a highly successful biomarker. Using the simulator still helps understand its performance across different scenarios, especially if the prevalence of amyloid positivity varied in different populations. It shows that even in very successful cases, understanding the nuanced performance with tools like OAP is valuable. Then they tackle predicting whether someone will respond to antidepressant medication. Studies suggest that some neurocognitive predictors might explain about 20% of the variation in how well someone improves. Again, the paper shows that even with this, the actual prediction of who will respond and who won't is only moderately good, especially once you account for the base rate of response, which is about 15% beyond placebo, and the reliability of brain activity measures. They emphasize that a big problem is often dichotomizing outcomes, like calling someone a responder or non-responder, which loses a lot of information and makes prediction harder. They also have tools within the simulator to explore how combining multiple biomarkers can improve predictions. The idea is that a stronger, more reliable single marker might be better than many weak, unreliable ones. They show with an example that to reach a high level of predictive accuracy, like a PR-OC of 0.8, you might need a lot of predictors if they're only moderately effective, but achieving a similar level of accuracy could be possible with fewer if those predictors have larger effect sizes. This points to a strategy of seeking stronger biological signals rather than just accumulating more data. Here they look at predicting who might develop psychosis. A specific brainwave pattern called MM has shown some promise. They analyzed studies showing an effect size of around 0.43 in individuals at high risk for psychosis. When they plugged this into the simulator, considering the rate at which people actually convert to psychosis, and the test's own reliability, the predictive power ends up being modest. It offers some added information, but it is far from being a perfect predictor on its own. This also leads to a discussion about how the initial screening for high risk might be missing the majority of people who will eventually develop psychosis, suggesting that improving those initial screening methods might be an even bigger hurdle. Finally, they examine predicting suicide attempts using electronic health records. This is a high-priority area for AI in mental health. They looked at a large study that found a notable accuracy, ROCOC, of 0.71 minus 0.73. However, the simulator reveals that with the relatively low base rate of suicide attempts in the population, this accuracy translates to a very low positive predictive value. This means that when the model flags someone as high risk, there is a good chance they won't actually attempt suicide. They conclude that while these tools can help identify some cases, the fundamental challenge of low base rates in the general population makes universal prediction very difficult, and perhaps broader prevention strategies are more critical for reducing suicide rates. So, to wrap things up, this paper really drives home the point that statistical significance is not the same as clinical usefulness. They've given us a powerful tool, the E2P Simulator, to help researchers and clinicians better understand the real Zen-world predictive value of biomarkers and prediction models. They found that even good Zen-sounding effect sizes can lead to modest real Zen-world outcomes. if we don't account for factors like how common the condition is and how reliable our measurements are. They strongly suggest that improving measurement reliability and focusing on finding larger effect sizes are key to making progress in precision psychiatry. It is important to remember that no single number tells the whole story. While they highlighted the limitations of ROCOC and the strengths of PROC and net benefit, each metric has its uses and downsides. ROCO, for example, is good for comparing how well different tests can distinguish between groups regardless of how common the condition is. But for practical decisions, you need to consider the base rates. Net benefit, which is part of clinical utility, requires making some tough choices about the costs of false alarms versus missed cases, and these costs can vary. The paper emphasizes that a thorough evaluation needs to use multiple complementary metrics. They also made a distinction between discriminative effects, which are about differences between groups, and causal effects, which are about the impact of an intervention. The E2P Simulator is for understanding those discriminative effects, which are what we use to build prediction models. Now, no study is perfect, and this one is no exception. The E2P Simulator currently relies on simplified models, assuming that data follows a normal distribution. Real-world data can be messier. Also, it doesn't automatically account for the uncertainty that comes from having a limited sample size. Although you can input confidence intervals to get a sense of that, and it is currently focused on simple yes-no predictions, not more complex scenarios like predicting multiple types of outcomes or over time. So, what does all this mean for us? It means that when you hear about a breakthrough biomarker or a new prediction tool, it is crucial to ask questions beyond just, is it statistically significant? Or how accurate is it in the lab? We need to ask, how reliable are the measurements? How common is the condition in real life? And how likely is this tool to actually help me or a loved one make better decisions? The E2P Simulator is a fantastic step towards making these critical questions easier to answer. It empowers researchers to be more rigorous and helps translate exciting scientific discoveries into tools that truly benefit people. It reminds us that the path from a lab finding to a clinically useful tool is long and requires careful consideration of the real world. And that is it for today's dive into the fascinating world of scientific translation. If you found this helpful, please give this video a big thumbs up, leave a comment below with your thoughts or questions. And don't forget to subscribe to RUBIN'S Mind Lab, so you don't miss our next deep dive into the science that shapes our minds and lives. Thanks for watching, and I'll see you next time.